These are the 4.21 video notes, and we're going to be starting rational functions today. Rational function is a function in the form of r of x is equal to p of x over q of x, where p and q are polynomial functions and q is not the zero polynomial. The domain of a rational function is the set of all real numbers except for those in which the denominator q is zero. So we've looked at this before. We've looked at it with transformations in class, and when we looked at it with transformations, they called it a reciprocal function. That's another name that we can kind of go for with rational functions, but reciprocal functions tend to be much more just when we're looking at that parent function of 1 over x. Rational functions kind of encompass a much larger scope of things. So rational functions is basically the idea that we can have a polynomial on top and a polynomial on the bottom. And then especially once we start getting into polynomial functions which are different, I would say that a reciprocal function kind of mostly resembles like a very specific type of rational function. And it's one of those things where it's like all squares are rectangles, but not all rectangles are squares. Or all reciprocal functions are rational functions, but not all rational functions are reciprocal, because reciprocal has that like very clear hyperbola shape across the asymptotes, while a rational function can start taking on a lot of different forms and a lot of different shapes. I wouldn't say that there's oblique asymptotes, and we're going to learn about things like that with a reciprocal function. So the biggest thing that we need to know is that a rational function is a polynomial on top and a polynomial on the bottom. And we have to define this as well as saying that there needs to be a variable in the denominator. We've seen this before. So again, if I were to say f of x is equal to 2x minus 7 over 3, this is a polynomial, because I can rewrite this as 2/3 x minus 7/3. This is just a linear equation. So that's a polynomial. The variable's not in the denominator. If I write out f of x is equal to 2x squared minus 3 over x cubed plus 7, this is a rational function because of that variable in the denominator. If there is no variable in the denominator, it's just going to be a polynomial. We are just writing out a common denominator between two terms, and we're dividing out that number. For a rational function, there has to be a variable in that denominator. If not, it's more than likely just a polynomial. Domains of rational functions, we've done this a million times. We've looked at the domains of rational functions literally 3 or 4 times already in class. Now we're just looking at it again, specifically in relation to a rational function. We've got that variable in the denominator. We've got a fraction here. We have to remember we can't divide by 0. We even have this up in the rules where your denominator q cannot be 0, all real numbers except those where the denominator q is 0. If we get a value of 0 in our denominator, we cannot perform a mathematical operation. It simply does not exist. So we set our denominators equal to 0 and we solve. So to find the domain of a, I look, my denominator is x plus 5. I set x plus 5 equal to 0. I get x is equal to negative 5. So my domain is all values of x where x cannot be equal to negative 5. It's that straightforward. Again, b, I've got a denominator here. X squared minus 4 is equal to 0. X squared is equal to 4. X is equal to the positive negative square root of 4. X is equal to positive negative 2. So my domain here is all values of x where x cannot be equal to positive negative 2. For c, this one's a little bit tricky, and we intentionally, as math teachers, as math textbooks, put this one in to see if you're paying attention and also to know if we understand what's going on with this math. I get x squared is equal to negative 1. I get x is equal to the square root of negative 1. And this is imaginary. And since this is an imaginary number, this isn't a real number, this doesn't have any effect on the domain. So we don't say that this is all values of x with the exception of the imaginary number 1. That's not how that works. We are talking about all values of x. So here your domain is just going to end up being all real numbers. We could also define it like this, where we're just saying it's all values of x. negative infinity to infinity, etc. And then finally, we've got our last one here, x minus 1 equals 0, x is equal to 1. Therefore, this is all values of x, where x cannot be equal to 1. All right, so I'm going to go ahead and I'm going to say that we should know this. This is something that at this point in the year we should clearly know. I can understand if we have to factor our denominator to find our domain, but if we're struggling to find these domains, this is something that we've been looking at since August. So we really need to make sure that we're aware of what we're doing here. It's really straightforward. You set your denominator equal to 0 and solve. I can understand sometimes when we factor, we might factor wrong. I can understand that there are some that seem a little bit more complicated, but we've been doing this on multiple tests and quizzes. We've been doing this in multiple different units, multiple different sections. We need to have this solidified by now. All right, now a vertical asymptote. Vertical asymptotes are one of the domain exceptions that we can have. So here, let's go ahead and look at this function. I've got y is equal to x squared plus 1 over x plus 3 over x minus 1 squared. Right away, I can say that x minus 1 is equal to 0, x plus 3 is equal to 0, x is equal to 1, x is equal to negative 3. So I've got all values of x where x cannot be equal to 1 and x cannot be equal to negative 3. When we look here, we can see that, okay, at these exceptions, at these values, I've got vertical asymptotes. Now, I'm going to show you a lot of things on Desmos in class when we get together again. I want to make sure that we're looking at this, and I'm going to explain some things on Desmos so you can see this more. A vertical asymptote is not really there. We draw it as dashed lines on graphs, and you see them as dashed vertical lines here. They don't exist. Vertical asymptotes aren't part of the graph per se. They're much more kind of, we draw them in to represent a behavior that the graph takes on. So as our graph changes, as we have these exceptions, as we have our graph behave, we have these asymptotes. Now, we make these asymptotes because graphs start following asymptotic behavior. We can see here where this graph gets really, really close to this value, and it keeps going up and up and up, or down and down and down, as it approaches each specific asymptote. So again, these aren't real things. I'm going to show you on Desmos how if I graph this on like a normal graphing technology, it doesn't bring up a vertical asymptote. We can draw them in graphs by hand, and we've been doing this for years and years and years, and this is to help mathematicians along, help give them a visual so that way as they're making this, they can make things a little bit clearer. But what we're saying is that at these two values where it doesn't exist, because of the nature of our function, our graph approaches these values and they get really close to the values, but they never are quite the values. So they just kind of follow along this vertical pattern, and they get slightly closer and closer and closer to this like invisible line on the graph. But when we graph it by hand, we have these actual dashed lines that we put in vertically. And again, I'm going to show you more of this on Desmos when we're in class again. I want to make sure that we have this down, that we understand what's going on. I'm just giving you an idea of what a vertical asymptote is. It's an invisible concept that we represent via a dashed line, where the graph will get close to that asymptote and will follow along it, but it will never cross it. It never, ever crosses a vertical asymptote. So to find a vertical asymptote, this is where it gets a little bit, I'm not going to say difficult, but we have to pay attention. We have to be aware of what we're doing. You might think, based off that previous example, that every vertical asymptote is a domain restriction, but that's not actually the case. In rational functions, there's two types of domain restrictions we can have. We can either have a vertical asymptote or we can have a hole. So a hole in the graph just means a point that can't be graphed. I'm going to show you this in class on Desmos so that way you can get a better idea of what that is. Well, how do I figure out what is a vertical asymptote versus what is a hole? Well, that's where I'm going to have to pay attention to my denominator, to my numerator, to everything that's going on. So we're going to go through and we're going to look at the examples that we've already done on finding domain and look at how to figure out what is a vertical asymptote versus what is a hole. For A, I already know that my domain here is all values of x, where x cannot be equal to -5. And my goal is to figure out, is x not equal to -5? Do I have a hole in my graph at -5, or do I have a vertical asymptote at -5? Those are my only two options with a rational function. It's one of those two things. So what I have to do to figure that out is I'm going to factor it. I'm going to say f of x is equal to 2 times x squared minus 2, all over x plus 5. I could theoretically factor this more. Let's go ahead and just say that this is x plus the square root of 2 times x minus the square root of 2, because this is a difference of squares, and I put this over x plus 5. I can't cross anything out. This is not simplest form, but I cannot cross out any factors. I don't have any factor in common with my numerator and my denominator. 2, x plus the square root of 2, x minus the square root of 2, and x plus 5 are all distinctly different. So because I can't cross anything out, because I just have x plus 5 remaining on the bottom, this means I've got a vertical asymptote at x is equal to -5. That domain restriction ends up being my vertical asymptote. Let's go ahead and look at B. I can factor B. I can see with B that I've got this value of 1 over x plus 2 times x minus 2, because again, I'm talking about a difference of squares. But again, nothing crosses out from my numerator to my denominator. I've got no multiplication happening. I just have 1 on top. So because of that, I can just right away say, all right, my denominator remains the way it is. My vertical asymptotes are at x is equal to positive -2. At both positive and -2, I'm going to have that vertical asymptote. I'm going to have my graph behave in that way. With C, my domain was all real numbers. If I have a domain of all real numbers, I can right away say that there's no vertical asymptotes. If you have any domain that is all real numbers, it's just impossible. The only place that a vertical asymptote is at a domain restriction. It can't exist at that value. So if we have a graph that can exist at all values, we don't have any vertical asymptotes. D is going to be the one example where we will find holes. And here's how I know that. I'm going to factor my numerator, and my numerator becomes x plus 1 times x minus 1, because I'm looking at a difference of squares. Oh, would you look at this? These cross out. I'm allowed to cross these out because on my numerator, I've got multiplication, and then this entire thing is set up as division. So since I have multiplication over division, I'm allowed to cross out these two factors. They don't exist, they cross each other out. Well, the thing is, I still have this x minus 1 in the denominator. This doesn't go away. This does not become f of x is equal to x plus 1. Kind of does, but still I have to reference the fact that I had this denominator to begin with. I had that polynomial in my denominator of this fraction of this rational function. So I still have to acknowledge the fact that my domain in this case was x can't be equal to positive 1. But in this case, I've got a hole at x is equal to positive 1, and I've got no vertical asymptotes because I had no other factors in my denominator. So here is where we figure out what is a hole versus what is a vertical asymptote. If you can cross out a factor with your numerator, if a factor is both in your numerator and your denominator, and you are allowed to cross them out, it's multiplication over division, then what you have is a hole at the graph. And we are going to look at this at Desmos, and we're going to see how basically I could rewrite this as saying that this entire function is x plus 1 times x minus 1 over x minus 1, which is just equal to 1. So I'm basically multiplying one function by 1, but that 1 that I'm multiplying by gives me a domain restriction. It puts this hole in the graph, and it makes it so it just doesn't exist at this singular point. The entire graph is going to look like the linear function x plus 1. It's just not going to exist at the value of x is equal to 1, which might be something it's kind of hard to wrap your head around right now, but we're going to look at it on Desmos as a class the next time we're together, and I think that should clear some things up a little bit more. All right, you guys have a homework assignment tonight. All you need to do is just find the domain and the vertical asymptotes. So list the domain and list the vertical asymptotes for each, so you have to pay attention to your factors. You have to pay attention if you can cross out your numerator and your denominator. Remember, if a factor crosses out between your numerator and your denominator, you're looking at a hole. If you have just a factor in the bottom that can't be crossed out, that is going to end up becoming a vertical asymptote. If you have any questions or concerns, please reach out and have a great night.